Welcome back. The objective of this video is to explore end behaviors of logarithmic functions. We'll look at concavity of logarithmic functions, and we will complete an application problem of a logarithmic function. So let's take a look at example 4 here. Given the function y equals log of x minus 1, determine the asymptotes, the end behavior, and then we'll use limit notation to describe that end behavior. So in this first graph here, I've taken the liberty to just sketch a graph of log x, where we've got our point through 1, 0. We've got our vertical asymptote at x equals 0. That's kind of our standard or our parent logarithmic function. So in example A here, log of x minus 1, we're simply shifting that logarithm function just 1 unit to the right. So that one now is going to pass through the point 2, 0, and we'll have a vertical asymptote at x equal 1, and our graph will look something like that. So our vertical asymptote shifts 1 unit to the right, goes from x equals 0 to x equal 1. It's going to pass through the point 2, 0 instead of 1, 0. And then our end behavior, the limit of y as x approaches positive infinity, well, that's going out to positive infinity. But the limit of y as x approaches our asymptote here at 1, and we're going to approach 1 from the right-hand side, that is then going to negative infinity. So the important thing here is that x approaching 1 from the right is recognizing that. So that this bottom part of our limit notation, pay close attention to that. Looking at y equals log of 2 minus x, well, we could rewrite that as the equivalent of log of the opposite of x minus 2. So what that's going to do, it's going to take our horizontal asymptote, it's going to shift it 2 units to the right. So we have a new horizontal asymptote at x equal 2. But instead of graphing our logarithm to positive x's, now our x's are going to get reflected across. So we would normally go through what would be 3, 0. Now we're going to go reflect the other way, and we're going to go through 1, 0 again. But now our graph is going to look something like this, because we're reflecting all our points over that new horizontal asymptote, or our new vertical asymptote. So that vertical asymptote occurs at x equals 2. The limit of our function y, our limit of our function y as x approaches 2 from the left-hand side is negative infinity, and our limit of our function y as x approaches negative infinity is positive infinity. In C, where we have y equals 2 minus log of x plus 4, now our vertical asymptote is going to be shifted 4 units to the left, so that's going to become x equals negative 4. So x equals negative 4. And our point that was at 1, 0 is going to be shifted 4 units. It's going to go to negative 3. But the 2 is going to shift us up 2, so that's going to be shifted up here to positive 2. Let's see how that, but then I have the opposite of that's 2 minus log, so that minus sign here is also going to be a shift on the y-axis as well. See how that looks. So our new 0 line, if you will, is going to occur at y equals 2. And our points now are reflected, instead of graphing a normal logarithm curve where we're increasing, now with this negative sign, our logarithm actually is going to be decreasing, and it's going to look something like that. So this is the graph of our logarithm. So now we can take a look at what our limit of y as x approaches positive infinity. Well, that is going out to, our y values are going to positive infinity. Let's see if I have that right. I don't think I do. No, I have that right. And the limit of our function y as x approaches, now we're going to approach our horizontal asymptote, -4, from the right-hand side or from the positive side, and that is going up to positive infinity. And then in D, y equals log of x minus 3. Well, all this 3 does is take our 1, 0 point of our logarithm and shift that down 3 units, and our graph is going to look something like this. So A and D should have a lot of the same information. We're not shifting our vertical asymptote anywhere, so our vertical asymptote is going to stay at x equals 0, and now the limit of our function y as x approaches positive infinity is going to positive infinity, and then the limit of our function y as x approaches, we're going to approach our horizontal, our vertical asymptote, I beg your pardon, our vertical asymptote 0 from the right hand side, and that is going to negative infinity. In example 5a, it asks us to use the table of values to determine whether the function is increasing or decreasing and the concavity, and make a sketch. Can you determine the domain of the function? So let's graph the easy ones. Let's graph 2 on the x, 0 on the y. We'll plot that guy. 6 on the x, 1 on the y, and 26 on the x, 2 on the y. Well, that's going to be way out there. 500 on the x, okay, and then 1.01 on the x, and negative 2.86, that'd be negative 3, so that'd be about right there. So we get a picture of what our graph is looking like. It appears that we have a vertical asymptote at x equals 1. So our function is f of x is increasing. It's concave down. The rate of change, though, is decreasing. And our domain goes from 1 to infinity. In B, we'll graph the easy ones again. So we have negative 1 on the x, 0 on the y, 1 on the x, negative 1 on the y, 7 on the x, negative 2 on the y, 500 on the x, negative 5 point something, 5.66, and then negative 1.9 and 2.10. So it appears we have a vertical asymptote at x equals negative 2. So f of x is decreasing. Our graph is concave up. Our rate of change is increasing. It's still negative, but it's less and less negative. So rate of change is increasing, and our domain are all x's from negative 2 to infinity. In example 6, they ask us to complete this application problem. A principal P is invested at 6.25% compounded continuously and increases to an amount K times the original principal after 2 years, where T is equal to the natural log of K over 0.0625. So they gave us some K values here. These are going to be our inputs that we're going to input into this function, and we want to find the T, the outputs. So if we're continuously compounding, you might recognize that as, hey, maybe we could use PERT here. But complete the table and determine how long it takes for your investment to double. Hopefully some of you guys are going, well, I can use the rule of 72, and 6.25% times some T equals 72. This is going to be probably less than 12 years to do that. So hopefully we come up with something a little less than 12 here. But we'll go ahead and use our calculator. We'll put K values of 1 and 2 and 4 and 6 and 8 in our calculator and see what we get. So go to my calculator. I do the natural log of 2 over 0.0625. I get 11.09. Again, I can do the natural log of 4 divided by 0.0625, and I can get the values to complete my table. So let's go back and complete that table. So the natural log of 1 over 0.0625 is going to be 0. The natural log of 2, we already saw that. That's 11.09. And 4 is 22.18, and so forth. So our investment is going to double at 11.09 years, which is consistent with our rule of 72. We said it would take less than 12 years. So it's going to double after 11 years. It's going to double again after 22 years. And then it's going to double again at K natural log of 8 at 33 years. Okay, so every 11 years it's going to double. We can use our graphing utility to graph the function. We can make our K values, we'll input those in list 1. We'll put our T values, we'll put those in list 2, and do stat, calc, and exponential, and then we would get a function as well for what those are. So what that looks like on your scatter plot, we have K is 1, Y is 0, K is 2, we get 11.09, K is 4, we get 22, and so forth. So I've got a scatter plot that looks something like this, and I can get some sort of exponential function that will look like that. In fact, I probably wouldn't do an exponential function here. We would do a logarithmic growth function here with this. Try a log function, see what you get. But plotting our points, that's going to be our graph. And then in C, suppose you had $1,000 to invest. Your function would be 1000 e to the 0.065t. You might recognize that. That is PERT, where the $1,000 is our principal, e raised to the rt. So that's our continuous compounding. We would go ahead and put 11.09 in for t, and we get $1,999.96, and our money does indeed double. So there's some examples. With logarithmic functions, we've worked on n behaviors and did an application problem and saw a little review of the Rule of 72. And we'll get some more practice with this when I see you in class.